My name is C. Chatterjee. I'll be teaching you inorganic chemistry. So today is the first lecture of inorganic chemistry. We'll start with the periodic table. What I request you to do is that for my lecture, use a separate notebook and Xerox a periodic chart with electronic configuration. That will be easier for you to understand inorganic chemistry because you know that electronic configuration plays a very important role in understanding the chemical properties, the physical state of the matter, how the electronegativity or electropositivity is to be accounted for any element. So the periodic table is very important, and Mendeleev has contributed a lot in understanding inorganic chemistry by devising a periodic table. Earlier, the periodic table was known in the short form of the periodic table, that is group 1 to 8, and the inert gases or the rare gases were known as zero group elements. Now, inorganic chemistry deals with atomic number 1 to 103. So, inorganic chemistry has to deal with a diverse element. As a result, the properties will be quite diverse. One rule cannot explain everything for all the elements. There will be a variation, there will be an exception. And in inorganic chemistry, an exception is rather a rule rather than an exception, because it deals with a large number of elements with having different electronic configurations. And so we have to understand the importance of electronic configuration and understanding inorganic chemistry. While distributing the 103 elements in the periodic table, earlier the short form of the periodic table was subdivided into A and B category. Like group 1A was alkali metal. Similarly, 1B was copper, silver, gold. Those were included in the group 1B. Similarly, group 2A was ascribed to alkaline earth metals, beryllium, magnesium, calcium, strontium, barium, and radium. Similarly, group 2B was included for zinc, cadmium, and mercury. And that was the proposal given by European School of Chemists, which the international body, the IUPAC, the International Union of Pure and Applied Chemistry, that is the body which finally gives an approval to the name of an element, the symbol of an element, its position in the periodic table, and the nomenclature of inorganic and organic compounds. But there was a problem, the problem created by the Americans, which Europeans classified as A and B. Americans just reversed it, and as a result, the controversy arises because which author book you read. Okay, if you read an American author, it will not match with the European convention. And as a result, the controversy was going on for years together, till 1989, when IUPAC came into picture and said, enough is enough, no more controversy, and they describe or group the elements from 1 to 18. So there is no A and B subclassification, so there is no confusion, and that is what is now being known as long form of the periodic. Elements can be classified. Today, what I will do is first I will start with the classification of elements, followed by the classification of compounds, how the compounds can be classified, and that will be after the classification of elements. So the elements 1 to 103. Everybody knows that the element number 1 is a hydrogen, and 103 is Lorentz. But today, very recently, you must have seen in the newspaper that they have, the German scientist has claimed that he has synthesized an element number 918 by bombarding californium, which is having 98 atomic number, bombarding with calcium 20, and straight away got an element with an element number 118. Now, if you see the periodic table, the 103 element, the element number 103 Lorentz, where the 5f electrons are filled up, the 5f orbitals are completely filled, and one electron in the 6d and two more electrons in the 7s are there. Now, if you go back and see the periodic chart, you will see that 9 more electrons will be added to the d orbital, 6d orbital. Okay, that will give the 110, and 6 more electrons will be added to the p orbital. Okay, because you have S2, you have P6, and that will end the electronic configuration. Up to, if you know, up to 103, that is good enough. Although JE syllabus says that electron up to 1 to 36 are included in the JE syllabus, their chemical properties, physical properties, but if you know the groups and the periods are the horizontal lines, the groups are the vertical lines, and you should know that which group belongs to which element. First is that group 1, 2, then 3 to 10, 12, then 13, 14, 15, 16, 17, 18. Group 1 represents the alkali metals, group 2 alkaline earth metals, group 3 to 12 includes transition metals, 3 to 12 includes transition metals, 13 boron, aluminium, gallium, indium and thallium. They belong to group 13. Similarly, carbon, silicon, germanium, tin and lead, that belongs to group 14 elements. Nitrogen, phosphorus, arsenic, antimony and bismuth. The 15th group, oxygen, sulfur, selenium, tellurium and polonium. That is the 16th group, fluorine, that's the 17th group element, and 18th group will consist of helium, neon, argon, krypton, xenon, radon. Then that is how the 103 elements have been distributed in the long form of the periodic table. If I want to know the valence electron, how many valence electrons, the outermost electrons are there. Okay, 1 represents 1, 2, 2, no problem. But 13, you ignore 1, that 3. That means boron has 3 valence electrons. When you go to carbon, 14, you ignore 1, 4 valence electron. 15, 5 valence electron. 16, 6, 17, 7, 18, 8 valence electron. Okay. In between, you have the inner transition elements, and we will discuss that what are the characteristics of inner transition elements, what are the inner transition elements. Even now, the position of the hydrogen in the periodic table is not clearly understood. Where should it be placed in the periodic table? Someone suggested that, okay, since hydrogen forms H plus very readily, So hydrogen should be above alkali metals because alkali metals form +1 cations. Somebody says no, hydrogen also forms H minus hydride, so it should be placed under above halogen. And somebody said no, the electronegativity of hydrogen and carbon don't differ a lot. Carbon is 2.55, hydrogen is 2.2. So hydrogen should be above the carbon. But still that problem has not been resolved yet. And that is why the hydrogen and the helium, they are placed somewhere on the top of the periodic table and don't think that they belong to any group or any above any group. Now we go to classification of elements. Elements can be classified broadly into 4 categories: representative elements, transition elements or transition metals, inert transition elements or inert gas. Now we'll discuss one by one. First, the representative elements. The representative elements have the outermost electronic configuration NS1 to NS2 p5, and they include metals, metalloids, and non-metals. So these 3 types of elements belong to representative elements. The metalloids are silicon, germanium, arsenic, antimony, selenium, tellurium. These 6 are metalloids. The metals include group 1, alkali metal, group 2, alkaline earth metal, aluminium, gallium, indium, thallium, tin, lead, bismuth, and polonium. They are the representative. First, let us discuss about the metals. Representative metals. Representative metals have 2 types. One, highly electropositive metals like group 1, group 2, aluminium. They are highly electropositive metals. And some are not so highly electropositive like tin, lead, bismuth, polonium. They are not highly electropositive. So, the group 1 metals and group 2 metals, the alkali and alkaline earth metals, they form ionic compounds because their electronegativity is less, the electropositive character is very high, so they easily lose the electron to form cation. Similarly, aluminum also highly electropositive. It loses 3 electrons to give you aluminum 3+ ion. These metals have varying strengths. The tensile strengths are varying, the hardness varies. We know that the alkali metals are the softest metals. Why they are softest metals? What is the reason for being soft? So, the strength of a metal is determined by the metallic bond strength. Metallic bond strength determines the cohesive force exists in a metal. Higher the cohesive force, stronger is the metal. Stronger the metal, higher is the boiling point, higher is the hardness, higher is the metal. So boiling point, melting point, hardness is a reflection of metallic bond. Chemistry as a subject normally treated as a subject of remembering and not logic based, which is absolutely wrong. Sure, there are things which it is a combination of facts and logic. You can't ignore the facts. Okay, just like first law of thermodynamics, you can't prove. You have to take it as it is. Okay. Similarly, potassium permanganate, all of you have seen, is violet in color, purple in color. So that it could have been yellow, it could have been green. but you have to remember potassium permanganate is powerful. So certain facts have to be remembered, and I will try to rationalize as much as possible for inorganic chemistry. In inorganic chemistry, there is not a one-line direction that one argument will always hold good for every case. You have to have different options depending upon the experimental results. You have to provide a mechanism by which you can make the experimental results the best possible. So, the metallic bond strength. The metallic bond strength depends upon the number of electrons contributed by the individual metal atom. So the metal, when alkali metals, if we look at the alkali metals, they have only one outermost electron. The alkali metal can donate only one electron per atom. And since that is the least number of electrons contributed per atom, that is why the alkali metals are the softest metals. Now, when you go from alkali metal to alkaline earth metal, the hardness increases, the melting point increases, because now per atom you get 2 electrons per atom, which is going into the metallic bondage. So what is metal? How do you view the metal? You view the metal and the metal ion acquires the lattice site. The electrons contributed by the metal forms a sea of clouds, a pool of electron cloud, and there is an attraction, electrostatic attraction between metal ion and the sea of electron cloud. Now, greater the charge, more the number of electrons, greater is the electrostatic force of attraction, and as a result, the metallic bond strength increases. When you go from alkaline earth metal to aluminum, it increases further because aluminum has 3 valence electrons, and as a result, it can contribute 3 electrons per atom. So the number of electrons in the electron cloud is increasing. The charge on the metal ion is increasing, and we know that electrostatic attraction depends on Z1, Z2 by R square. So if Z1 is increasing, that is the charge on the metal ion is increasing, the number of electrons are increasing, so the electrostatic attraction will increase. That will increase the cohesive strength of the metal. The melting point, not all the metals are very high melting. For example, if you look at tin, which has a melting point 232 degrees Celsius, lead has a melting point 327 degrees Celsius. Now, lead is a heavy metal. It has an atomic number 82. It has a mass number 208. It shows such a low melting point. That indicates that lead is a member of the 14 group element. It has an S2P2 configuration outermost. That means there are 4 valence electrons. And if all 4 valence electrons would have gone to form the metallic bond, then it would have been greater than aluminium, which has 660.5 degrees Celsius. So if aluminium contributing 3 valence electrons to the forming metallic bond gives rise to a melting point of 660, 232 and 327 definitely is much less. That means not all 4 valence electrons are going into the metal. They exhibit the low oxidation state, +1 or +2. They form an ionic compound. But not in inorganic chemistry, we'll see always an exception. For example, beryllium 2+ is a member of alkaline earth series. Beryllium doesn't form an ionic compound so easily. It forms a covalent compound. We know sodium chloride is an ionic compound. Calcium chloride is an ionic compound. Beryllium chloride is a covalent compound. Why they are ionic and how do I prove that they are ionic and this is covalent? Because what? How do I prove that beryllium chloride is covalent? If it is an ionic compound, beryllium, why the transfer of electron does not take place? How do you know the electron transfer has not happened? So ionic compound and a covalent compound can be distinguished if we measure the conductivity, not in the solid state. In the solid state, the ionic solids there do not conduct electricity because the ions are fixed at the lattice point. Yes. So when I melt it, the ions are now free, lattice energy is overcome, and now the ions conduct electricity. They are the charge carriers. So sodium chloride, calcium chloride, when I melt it, they conduct electricity, but barium chloride does not conduct electricity. That's a proof that barium chloride is a covalent and sodium chloride, calcium chloride is not covalent, they are ion. Now what makes it different? Beryllium and calcium, they are in the same group. But why beryllium behaves differently from calcium? Because of the beryllium and calcium, both of them have +2 charge. But beryllium has the smallest size. So charge to size ratio is known as ionic potential. And ionic potential is related to polarizing power. So charge to size ratio, if charge to size ratio, barium being the first member of the alkaline art series, so it will have the least size and +2 charge. The charge to size ratio will be maximum for beryllium. As a result, the polarizing power size ratio is related to polarizing power. Greater the polarizing power, greater is its ability to deform the electron cloud from its partner, leading to orbital overlap, leading to covalence. And that is why barium chloride is covalent. Calcium chloride is not covalent because calcium size is large. Charge is +, but size is large. As a result, the charge to size ratio is not very high, so the polarizing power is not very high. So if you see that melting point is decreasing, that's an indication that the covalency is increasing. For example, I will tell you, magnesium chloride and titanium tetrachloride. Magnesium chloride melts at 712 degrees Celsius. Titanium tetrachloride melts at -25 degrees. That indicates titanium tetrachloride is a liquid, magnesium chloride is a solid. What is responsible for such a large difference in the? As soon as you see a lowering point, normal, when I use the word normal, it means there is some exception. Magnesium ion size and titanium 4 are magnesium 2 plus and titanium 4 plus have identical size. Anion is common. But what about the charge? Titanium is 4 plus, magnesium is 2 plus. So charge to size ratio for titanium will be much higher than the magnesium. As a result, the titanium tetrachloride will be more covalent than magnesium chloride. And as a result, greater the covalency, lower is the melting point. Yes. The next, another example is sodium chloride versus Q plus chloride. Ionic size of sodium plus is similar to copper plus. Here the charge is the same, plus both cases. Size is the same, anion is the same. But look at the melting point. It melts at 800 degrees Celsius, it melts at 420 degrees Celsius. What causes such a large difference in melting? Size is same, charge is same, anion is same.
But electronic configuration of Cu plus.
What is that? Electronic configuration of Cu plus. What is that electronic configuration?
Pseudo inert gas.
Not pseudo inert gas. No. The D inert. Sodium ion has H2P6 at outmost level, isn't it? Because it has H2P6, H1 has gone, so the inert gas configuration is there. Whereas copper plus has 3D10 configuration. And the nuclear charge, the electron shields the nuclear charge. The nuclear charge arises because of the proton in the nucleus. The electron and the protons, they have identical magnitude of charge, but only the signs are different. So, if the electrons would have neutralized the positive charge or shield the nuclear charge of the proton in the nucleus, then what would have happened? Suppose you consider an element with atomic number 10 and you consider an element of atomic number 100. And if 9 electrons out of 10 would have shielded the nuclear charge effectively, 100%, then what the 10th electron would have experienced? How much of positive charge? Only one. If 99 electrons would have shielded the nuclear charge of 99 protons, then the 100th electron would have experienced how much of positive charge? One. Then both of them should have the same ionization energy. But is the ionization of the energy of an element remains the same? It varies. Why? Because different electrons react differently in shielding the nuclear charge. Now, Slater suggested a method to calculate the shielding constant of an electron. He proposed that S and P electrons shields the nuclear charge more effectively than D or F electrons. Now, as a result, since there are 10 D electrons in copper plus, due to imperfect shielding by the D electrons, the effective nuclear charge increases. What is effective nuclear charge? The effective nuclear charge is the atomic number minus the shielding constant. Then how much of electron with positive charge is being shielded or neutralized or screened by the electronic cloud. Since the D electron do not shield the electron nuclear charge effectively, so the value of S becomes small. So Z minus S becomes high, that is your effective nuclear charge. So when I cannot apply the ionic charge to size ratio, which I could apply in case of magnesium chloride and titanium chloride, I cannot apply the same argument for sodium chloride and P plus chloride. You see the difference in inorganic chemistry, that you have to keep your options open. Always not charge to size ratio is going to give you the result. When the charge is the same, size is the same, then I have to look for an alternative. And what alternative do I have? The effective nuclear charge, which arises due to imperfect shielding by the D electrons. So, because of that increased effective nuclear charge, the electron attracting power increases and Q plus chloride becomes more covalent. But is always covalency results in lowering of melting point? If it exists as an individual molecule, like carbon tetrachloride, carbon dioxide, methane, they exist as an individual molecule. So they are either gases or low boiling liquid. But silica, quartz is a high melting. Diamond is a covalent compound, has the highest melting point shown by an element. Okay? Silicon carbide is another compound which is called carborundum. Shows a very high melting point, very hot. Okay? So what causes these covalent compounds to be different from the normal covalent compound, like where it exists as a discrete molecule, an individual molecule? Because those three cases which I mentioned, diamond, quartz, and silicon carbide, they form a polymer. They don't exist as individual molecules. They exist as a polymer. They form a three-dimensional network structure. So when a covalent compound exists as a polymer and exhibits a network structure, they will be high melting, hard, high boil. So not necessarily all covalent compounds will be low melting or gaseous or low melting. It could be a very high melting solid like graphite, which is a polymer. It doesn't form a three-dimensional network structure, but it's a polymer. It forms a two-dimensional structure, layer structure. Silicon carbide, silica, they form a three-dimensional network structure. So they are responsible for their hardness. That is why they are hard. That is why they are high melting, high boil. Now, so when the metals in a low oxidation state, when I say the metal in a low oxidation state, they form ionic compound because I mean their polarizing power is not high because the charge is not large. As a result, they form ionic compound. Their polarizing power is low because the charge is limited to +1 or +2. But as soon as you go to higher valent metals, like aluminum chloride, tannic chloride, titanium tetrachloride, lead tetrachloride, okay, you can, for the time being, you can remove titanium because titanium is a member of the transition element. Aluminum chloride, tannic chloride, lead tetrachloride, they are covalent. Stannous chloride is a solid. SnCl2 is a solid, but SnCl4 is a liquid. Immediately you can guess why SnCl4 is a liquid, because tin has increased its charge from +2 to +4. As soon as you increase the charge, size decreases. Automatically, the charge to size ratio increases, polarizing power increases, covalency increases, and so it exists as a liquid. So the lower valent compounds will form an ionic compound. Lower valent metal compounds will form an ionic compound, but they are brittle. They are hard but brittle. Whereas in a higher valent metal compound, they form a covalent compound. Now we go to the oxidation state. Have you heard polarizability?
Yes.
Polarizability is related to size. Lower the charge, higher the size, higher is the probability, polarization. So, if an anion, mostly polarizability we ascribe to anions, not necessarily always, but normally we do. And greater the polarizability, higher is the covalence. So, as the size increases, the outer electron is far away from the nucleus, so the electron proton attraction decreases, so the electron cloud can easily be deformed, leading to orbital overlap. And that is why the greater the higher the probability, greater is the covalence. So between chloride, bromide, and iodide, the iodide is the most polarizable, and that will lead to higher covalence. Now the oxidation state of the representative elements shows two types of oxidation state. One is the group oxidation state, which is equal to the number of valence electrons. So the group oxidation state is equated with the number of valence electrons. So aluminum, the group oxidation state is 3 because it has a 2p1 configuration. It has 3 outermost electrons. Oxidation state, as observed, is group oxidation state -2. That means 2 unit lower than the group oxidation state. If you look at this lower oxidation state is due to inert pair effect. That what is inert pair effect? What is a pair? The pair is the pair of ace electrons. Since the ace electron has the largest penetrating power, so when an element has got an F electron, which is least effective in shielding the nuclear charge, the effective nuclear charge increases as the s electron comes closest to the nucleus. And as a result, the s electron ionization becomes more difficult, and so these electrons becomes inert, and since there are a pair of s electrons, so it is called inert pair effect. And where the inert pair effect is present, there you will see the oxidation state lower will be group oxidation state point, that is 2 units less than the group oxidation. This is observed in case of lead, helium, and bismuth. Helium has the atomic number 81, lead 82, bismuth 83. Before thallium, 57 to 71, the 14F electrons are filled, and 72 to 90, 80, the D electrons are filled, and then comes the P electron P1. So the thallium is 81, which has S2P1 configuration. Before that, there are 14 F electrons, there are 5 D electrons, and then because of the presence of the F electron, this is the most ineffective electron to shield the nuclear charge. They give rise to increased ineffective nuclear charge. And increased effective nuclear charge, due to increased effective nuclear charge, the S electrons come closest to the nucleus, and so they become inert, and that is why only one P electron is removed easily, and that is why they show only most stable +1 oxidation state. So thallium will show +3 as well as +1, because thallium has S2P1 configuration. It has 3 valence electrons, but only. So when it shows +3, it shows the group oxidation state. When it shows +1, it shows group oxidation state minus. Lead has S2P2 configuration. Same. 4F14, 5D10 is, now it is P2. So the group oxidation state is 4, but the group oxidation minus 2 will be 2. And lead shows +4 plus. Similarly, bismuth shows +5 plus, because bismuth has now S2P3 configuration. Now, due to inert pair effect, the group oxidation state becomes less stable than the lower oxidation, because S electrons have been stabilized. They don't ionize very easily. You can ionize it, but in that case, the system will be unstable. And what is the proof that system becomes unstable if I remove the S electron? Because the thallium +3, lead +4, bismuth +5 will behave like a strong oxidizing agent. What is oxidizing agent? Which accepts electrons. Why it accepts it? To come back to the lower, more stable oxidation state. So, since thallium-1 is a most stable oxidation state, 3 would like to come back to +1 by accepting electrons. Lead will accept electron to come back to +2 oxidation. And bismuth will come back to +3 oxidation state. So when the lower oxidation state becomes more stable than the group oxidation state, those are the elements in which the inert pair effect becomes strong. And those elements which are coming immediately after the filling of 4F electron, 5F electrons, and the D electrons. D electron is not that bad in a sense of shielding the nuclear charge. What is the proof I have to make such a statement? For example, if you look at tin, carbon, silicon, germanium, tin, lead. Tin shows +2 +4. Tin has an atomic number 50. It has 4d10, 5s2, 5p. There is no F electron. For tin, the +4 oxidation state is more stable than +2. What is the proof I have that +4 is more stable than +2? Because +2 would like to go to +4 by releasing electron. And which releases electron is a reducing agent. So a given oxidation state, if it is lower than the most stable oxidation state, then it will behave like a reducing agent. And a given oxidation state, when it is higher than the most stable oxidation state, it will act as an oxidizer. So lead 4 plus, bismuth 5 plus, they behave as a strong oxidizing agent. They are such a strong oxidizing agent that manganese 2 plus lead 4 plus in presence of acid goes to form permanganate ion, where manganese is 7 plus. So you see it's a 5 electron change. So it is such a strong oxidizing agent that it can oxidize manganese 2 to manganese plus 7 in acid medium. That proves that how unstable the lead is in the +4 oxidation state. Whereas lead 2 plus is quite stable, but not tin 2. Tin 2 plus acts as a reducing agent because its higher oxidation state is more stable than the tin 2 plus. So tin 2 plus goes to tin 4 plus by releasing electron, and that is why it acts as a reducing agent. Now, what is the difference between tin and lead? The F electron. Tin has d electron, 20 d electrons, but lead has F electron, which tin does not have. That clearly shows that how ineffective the 4f electron or the f electron is to shield the nuclear charge, which in turn increases the effective nuclear charge. As a result, its covalency is increased, its stability has decreased, and behaves like a strong oxidizing agent. Normally, the representative elements, the metals, the metalloids, and the non-metals, all of them. So where the F electrons are not there, the group oxidation state becomes a more stable oxidation state. But where the F electrons have been filled up, then the lower oxidation state, 2-unit lower oxidation state becomes more stable. So the representative elements can show only 2 different oxidation states, the group and 2-unit less than the group oxidation state, and nothing more than. The representative elements, when they form ions, they form colorless ions. It is sodium chloride is colorless, magnesium chloride is colorless, calcium chloride is colorless. Okay? All representative elements, when they form ions, they form colorless ions. But some of their compounds are colored. For example, tannic sulfide is yellow in color, arsenic sulfide is yellow, lead iodide is yellow, Pb3O4, which is called red lead, is red in color, and antimony sulfide is orange in color, lead dioxide is brown, stannous sulfide is brown. So they show some colors. Lead chromate is yellow, barium chromate is yellow. So some of their compounds are colored, not all of them, okay? But some of their compounds are colored. Now, at this moment, I am not going to tell you what causes the colors. When I discuss the transition elements, I will tell you that what causes the color of these compounds. In a nutshell, what can we say about representative elements? we can say that representative elements are the elements in which the outermost shell has got S1 to S2p5 electronic configuration. Some of them are metals, some of them are highly positive metal, some of them are not so highly positive metal like tin and lead, bismuth, polonium, gallium, indium. Some of the metals are hard, some of the metals are soft. That depends upon the number of electrons contributed by the individual atom. Greater the number of electrons contributed by the individual atom, the higher is the metallic bond strength, higher is the melting point, higher is the heart. Try to not only hear me, but try to rewrite as much as possible, because I read several books which you cannot afford to do it. Okay? So, more you, it is difficult, I understand that, you have to hear as well as write, but that has to be done. Because you won't find everything in what I discuss is available in the book. Something I read a higher level books, I take material from different sources, okay, and then I collate all this material and give the lecture. We can say that representative elements in the low oxidation, the metals when they are in a low oxidation state, they form an ionic compound. And the proof of ionicity is their conductivity in the molten state. They show two different oxidation states. The proof oxidation state, which is equal to the total number of valence electrons present in the system, and 2 units less than the group oxidation state, that is, the ace electrons which are present in their outermost shell are not easily ionizable due to the presence of the F electrons which do not